All right, today we are diving into something truly radical. We're talking about a completely new kind of computer, one that's designed to think like a human brain. It uses superconductors and light to power what could be the next massive revolution in artificial intelligence.
Okay, so let's just start with a really provocative question. What if the computers we've been building for the last, 80 years are just fundamentally the wrong tool for the job when it comes to creating real AI? I know it sounds kind of crazy, but the way we do things now has hit a major wall. And to really get why, we need to see how our digital machines stack up against, well, the original supercomputer, the human brain.
So here's the deal. Digital computers and our brains work on totally different principles. Computers are binary. Everything is a rigid 1 or a 0. The brain? It's analog. It works with a whole spectrum of values. Plus, computers have to constantly shuffle data back and forth between memory and processing. It's a huge bottleneck. In the brain, memory and processing are all mixed together. They're integrated. But the biggest difference, the real killer, is communication. Computers use these slow, clunky routing networks. The brain, though, has fast, direct connections. It's like its own built-in fiber optic network.
And that brings us to this completely new blueprint. Instead of trying to force our digital computers to act like a brain, which is awkward, what if we built the hardware from the ground up based on how a brain actually works? What if we could build a computer that thinks a little more like we do?
Now this right here, this is the core idea. The goal isn't just to write some clever software that pretends to be a neuron. No, the whole point is to build physical circuits that are neurons and are synapses. We're talking about creating hardware that operates like a brain on a fundamental level, not just faking it.
So how in the world do you even build something like that? Well, it turns out the answer is pretty wild. You combine two of the most exotic technologies we have, superconductors and light. These are the two secret ingredients for this whole new class of AI hardware.
Okay, so first up, you have the thinking part. That's all handled by superconducting circuits. These things are incredible. They have literally zero electrical resistance, which makes them insanely fast and ridiculously energy efficient. And they use these little things called Josephson junctions that act like super fast switches, which just so happen to be naturally perfect for the kind of math that AI thrives on.
But a brain is totally useless if its neurons can't talk to each other. And that's where light, or photonics, comes into play. I mean, light is the fastest thing in the entire universe, right? So it's the perfect messenger. You can use it to send a signal from one spot to thousands of others almost instantly, and it barely uses any energy.
So what you end up with is this really simple, super elegant system. The superconductors do all the heavy lifting, all the computation, and light handles all the communication, zipping information all over the place. If you think back to our brain analogy, the superconductors are like the gray matter, and the pathways of light, that's the white matter, connecting everything together.
So, we've got the blueprint. It sounds amazing in theory, but what's the actual payoff? How does this new approach really stack up in the real world? To figure that out, we've got to put it head-to-head with the current heavyweight champion of AI hardware, NVIDIA.
Let's really get into it. We're talking about a completely new way of doing things. So how does a single one of these great sky wafers, as they're called, compare to NVIDIA's latest and greatest, the GB200 superchip? Well, the results are, frankly, they're kind of staggering.
Okay, just take a look at this table. The new wafer is nearly 3 times cheaper, which is great, but that's just the warm-up act. The real magic is in the performance. Where NVIDIA is processing video at, say, 30 frames a second, this new hardware can process 60 million frames a second. That is 2 million times faster, and it does it all while using over 4,000 times less energy. It's insane.
But honestly, the single most important, most mind-blowing number on that whole chart is this one. 4,300 times more communication bandwidth. This is the critical bottleneck that's holding back AI right now, just getting the data where it needs to go. This technology doesn't just solve that problem, it completely obliterates it.
And what does that kind of speed actually mean for us? Well, this is the power you need for a self-driving car that can see and react to absolutely everything around it at once. Or for a doctor to analyze incredibly complex medical scans in a tiny fraction of a second. We're talking about the difference between an AI that takes hours to understand a video and one that can understand millions of video streams at the same time in real time.
So when you put it all together, the lower cost up front and the massive energy savings, the result is a 300-fold drop in the total cost of ownership to run a huge AI model. This isn't just a small improvement, it's a total disruption. It could make building these incredibly powerful AI systems accessible to way more people and companies, which is a game changer all by itself.
So that's where we are right now.
But the really mind-bending part of this whole story is where this technology is going. The roadmap here isn't just about making slightly better chips next year. It's about scaling up to systems that can rival the sheer complexity of the human brain. Let this one sink in for a minute. A single one of these wafers actually has fewer connections or parameters than a human brain, but it's so unbelievably fast that it could perform 65 times more raw operations every second than your entire brain. And that's just one wafer.
And the path forward is really clear. In about 5 years, the goal is to have full wafer-scale systems up and running. And then, in about 10 years, the plan is to link a bunch of these wafers together to create a single massive system with over 10 trillion parameters. We're talking about something that's truly approaching the scale of a human brain.
And here's the kicker. Unlike traditional silicon chips, where Moore's law is kind of running out of steam, this new technology has 4 different ways to keep growing exponentially. They can stack more computing layers on top of each other, they can add more wafers to the system, and they can develop smarter algorithms to take advantage of it all. It's like having 4 different Moore's laws all pushing forward at the same time.
So the end goal is this. We're on a path to a future where a computer with the raw power of a human brain doesn't need a data center the size of a football stadium burning gigawatts of power. No, it could fit inside a single office and run on a tiny fraction of the energy.
And that leaves us with one final, truly mind-bending question. We're not just talking about building a computer that's as powerful as a human brain. We're on a path to building one that operates 1,000,000 times faster. What kinds of problems could we solve with that? What discoveries could we make? That is the future this technology is trying to build.